Hi, my name is Alan, and I'm a graduate student in the Department of Systems and Computer Engineering from Carleton University in Canada. Today, I'm presenting a comparison of 2D localization using radar and LiDAR in long corridors. First, I'll be talking about the motivations behind the work done. Then I'll describe what radar scans look like. Then I'll talk about the methodologies for the comparisons, and then explain the experiment results. I'll wrap up with the conclusion and future works. Autonomous robots need to be able to localize themselves indoors where they don't have access to global navigation satellite systems and usually have to rely on a combination of exteroceptive and proprioceptive sensors to detect and track their surroundings. LiDAR sensors are often used for 2D indoor localization. One widely known failure mode of 2D LiDAR localization is in environments with simple geometry like the parallel lines resulting from scanning long corridors. Matching scans that are taken from a straight corridor produces large ambiguity along the direction of the hallway. Since long hallways are common in indoor environments, especially in commercial and large buildings, this becomes a significant issue with LiDAR localization. These issues are often addressed by fusing LiDAR systems with dead reckoning sensors like wheel odometry or IMUs, but dead reckoning accumulates large uncertainty over long traversals without exteroceptive sensor updates, and wheel odometry is sensitive to bumps and wheel slippage. Therefore, a method of detecting motion along the direction of the hallway using exteroceptive sensors is desirable. Millimeter wave frequency modulated continuous wave, or FMCW, fixed antenna array radar sensors are a candidate for such an application. These radar sensors are growing in popularity due to their small size, low cost, accuracy, and penetration ability. Similar to LiDARs, radars can also output point clouds of the surrounding environment. But radar provides point cloud detections based on how radar reflective the material is, which results in very different looking scans than from LiDAR. Metal structures are highly reflective, so they are detected much more strongly than less reflective materials like cardboard, drywall, or plastic. Highly reflective surfaces are also detectable even if hidden behind less reflective materials. The size, shape, orientation, and location of a surface strongly affects how well it's detected. These characteristics and the noisiness of the sensor makes the scans unintuitive to our eyes. In these plots, it's pretty easy to compare the LiDAR scan on the left to the picture on the right and recognize features in both. But that's not the case for the single or multiple radar scans. We want to take advantage of the different views the radar sees in order to localize in long corridors. Now that the LiDAR issues and radar scans are explained, here are the experimental objectives. First, we need a scan matching-based localization approach. Then, we want to compare the performance of this localization approach using LiDAR scans and using radar scans in a long corridor scenario. The localization approach works like this. An occupancy grid map represents the environment and is initially unmapped. The motion model predicts where the vehicle currently is using wheel odometry. When a scan is done, the scan is matched to the map, and the transformation between the scan and the map is used to correct the pose. Then the scan-matched scan is updated to the map and the process continues. The occupancy grid map is a grid of cells where each cell corresponds to a 3 cm by 3 cm area in the real world. The number in the cell and how bright it is the probability that something is occupying the cell, like a wall or furniture. Here is an example of a small grid map where we can guess that the dark bottom right corner is open space, the light area is a wall, and behind the wall is unknown. The odometry takes two wheel velocities and outputs a pose and pose covariance at every time step. The covariance is used to determine the size of the search space used for scan matching. When new scans arrive, the scan is transformed to many poses in a grid search pattern in a space around the odometry guess. At each point, the score of the candidate is done by taking all map cells with scan points in them and multiplying the cell values. The top scoring candidate pose is chosen to be the corrected pose, and the scan is updated to the map at this pose. The map update works like this. The inverse sensor model shown here determines the probability of a cell being occupied given a detection distance. This plot shows the probability for cells in the path of a beam from the radar or LiDAR, with the detected distance being 1.265 meters. On a map, the beam looks like these plots for LiDAR and radar, where a Gaussian blur is applied to approximate measurement noise. The difference between the two models are that LiDAR beams provide high confidence that the space between the sensor and the detected point is empty, but this is not the case for the radar due to the penetration ability, and therefore the radar only provides information on a detected point being occupied. The beams shown in the plots are added to the existing map using a binary Bayes filter, which incorporates new measurements into a cell in the map by summing the recursive or previous value of a map cell, the inverse sensor model value, and subtracting the prior or initial value. These values are converted from probabilities to log odds to enable the easy summation of these terms. A Turtlebot 3 waffle pi was used to gather the data for the experiments. The Turtlebot includes a 360-degree 2D LiDAR and differentially driven wheels with encoders. A Texas Instrument AWR 1843 millimeter wave FMCW fixed antenna array radar unit operating in the 67 to 81 gigahertz range was added to the Turtlebot. Ground truth for the experiments is recorded from Google Cartographer SLAM from the built-in robotic operating system on the Turtlebot. To collect data, the robot was manually driven around a hallway while recording wheel velocities, LiDAR scans, radar scans, and cartographer pose estimates. This plot shows the ground truth trajectory and also the LiDAR and radar scans projected from the ground truth. This plot shows us what the combined radar detections look like. The LiDAR scans usually show the straight hallway walls, but radar scans are clusters that may be doorways, window frames, or possibly metal structures behind the walls. Here's the results of using the localization scheme with the LiDAR scans and radar scans and odometry alone. It's clear that LiDAR scan matching is very poor along most of the hallways, particularly the straight sections. We can also see some small zigzags where the scan match results keep the pose in place when it should be moving forwards. On the other hand, the radar scan matching works quite well where it doesn't exactly follow the ground truth, but it is much, much closer. The RMSE values are shown in this table, which also shows that both radar and LiDAR scan matching can maintain accurate heading estimations. Here's a close look at the radar system localizing. The plot on the left shows scan matching, and the plot on the right shows the score distribution in a small area around the best results of the scan matcher. These score values are generated by sampling the scan match scores of poses drawn from a Gaussian distribution around the best score. The peak distribution shows high confidence along all pose dimensions. The distribution is peaked because matching between clusters of obstacles provides good pose information in the X, Y, and heading dimensions. On the other hand, with LiDAR, the score distribution is ridged, and there are multiple high-scoring candidates. This is because the shape of the scan is roughly two parallel lines, and with this type of scan, score results will not differ by much if the scans are translated up and down the map. Furthermore, with this scan matching scheme, even if the correct placement of the scan is down this hallway, this candidate would score poorly since some points will overlap on unmapped areas, which decreases the score compared to overlapping on mapped and occupied areas. So throughout this experiment, the following observations and conclusions were made. In long corridors, LiDAR scans are arranged in parallel lines, whereas radar scans are in clusters. This results in the scan matching performance of these sensors to be poor in one direction for the LiDAR, but confident in all dimensions for radar. A localization scheme based on scan matching would perform poorly with the LiDAR scans, but would be much better using radar scans in this environment. From these observations, we can see that a LiDAR system would heavily depend on another system to localize accurately, while a radar scan can be depended on for most of the trajectory in long corridors. Future works are to fuse LiDAR with radar since their failure modes are complementary and adding radar technology does not add much cost to any resource. Alternatively, radar is an exteroceptive sensor that may be capable of localizing with only an IMU, and since these sensors can be completely encased in a protective shell, this can make for a physically robust SLAM system resistant to most environmentally adverse conditions where camera systems or LiDAR systems may fail. Thanks for watching my presentation on localizing using LiDAR and radar scans. Bye.